Welcome to example number 10, called the Atwood's Machine Revisited. If you remember back in chapter 4, we studied the Atwood's machine, but we assumed that our pulley, just shown over here, was frictionless and massless. And that caused a situation where the tensions in both sides of the pulley were equal. However, now our pulley is, well, it has mass. We're going to assume that it's frictionless, but it has mass and has a moment of inertia, and which depends on its mass and its radius. So we're asked to find the acceleration of both masses m1 and m2. Okay, so the first thing we're going to need to do, just like we did before, is we're going to draw a free body diagram for m1, m2, and we're also going to draw a free body diagram for the pulley. Okay, starting with m1, we can draw a upward force acting straight up. That would be the tension acting on m1. Then we have the force of gravity acting straight down. And we'll label that force m1 times g, or you can call that the force of gravity acting on object m1. And then let's look at the free body diagram for m2 now. We'll have a tension 2, which is slightly smaller than tension 1. You'll see later on why. And then we have the gravitational pull acting on m2. And we'll label that force Fg2, or m2 times g. Now we should also look at the free body diagram acting on the pulley. Alright, moving on to the pulley, I've just drawn a similar diagram down here, and we want to show the forces acting on the pulley. So if you look at this string coming off this side, then we should have a tension T1 coming down, and then over on the right side we should also have a tension T2 going down as well. And we'll just label this T1 and T2. We also have a force of gravity acting right in the middle, which would be equal to the mass of the pulley times g. Next, I also like to show the direction of the acceleration. So we know that T1 and m1g, we know that force is bigger because this is going to accelerate up, m2, and m1 is going to accelerate downwards. So let's show that acceleration. We know that is accelerating upwards because this is a smaller mass than that. And these two accelerations are identical. Hence, if you look at the wheel is also going to feel an acceleration angularly in this counterclockwise direction. Next, let's apply Newton's second law, the linear version. Let's take a look at T1 and T2 and rewrite this in terms of Newton's second law. So if we take a look at m mass m1, and we apply Newton's second law, we'll use sum of F equals m1 times a. I'm going to assume that positive is going downwards in the direction of the acceleration. So therefore, this force of gravity m1g will be positive, and then this tension will be negative, and that will result in a net force acting downwards of m1 times a. If we look at mass m2 and apply Newton's second law, we can do that in a similar way. Sum of F equals m2a. In this case, I'm going to assume take the vertically straight up direction being positive, so the tension 2 will be positive and the m2g will be negative. So we have tension 2 minus m2 times g results in a net force of ma. So you can see our traditional two equations and two unknowns. However, when we saw this earlier back in chapter 4, we assumed that tension 1 and tension 2 were identical because their pulleys were assumed to be massless. But now they are not. They're not the same tensions. You see, tension 1 is slightly bigger than tension 2 that causes this wheel or pulley to rotate angularly. So now let's take a look at Newton's second law rewritten in terms of the angular quantities, meaning the torque. So if we look at the pulley, all right, we have the sum of the torques is equal to I times alpha of this pulley. Now there are two torques in here. We have the torque produced by tension 1, torque produced by tension 2. In fact, there's a third torque from this one, but we're going to be taking our axes of rotation about the center of this. So therefore, that torque produced by the weight of the pulley will be 0. Okay, if you recall our torque formula, our torque is going to be r times F times the sine of the angle between the radius vector and the force vector. So I've shown the radius here and the mass of the pulley included into our diagram. So if we look at the torque that's produced by T1, that's going to be producing a counterclockwise torque, which is considered to be positive. So we have T1 and R1. Well, R1 is really R, so let's just replace R1 with R, times the sine of the angle between the radius vector and the force vector, and that's going to be actually a 90 degrees, sine of 90. And sine of 90, if you recall, is just 1. We could just replace that just with 1 here. It'll really just be R times T1. We have the other torque, T2, that's causing the wheel to rotate clockwise, and hence that is considered to be a negative torque. So we have that as being multiplied by R2, or just R, because they're both being pulled at the same place on the pulley, same distance away. So it's R multiplied by T2. And this is equal to I times alpha. Now, what is I for the pulley? What kind of shape do you think that is in? Well, to make life a little bit easy for ourselves, we've assumed that the pulley is a uniform disk. So we need to look up the rotational inertia of a disk. Earlier in our notes, we have a table of common geometric shapes, and we can find the disk right over here, or solid cylinder, and the rotational inertia is given by 1/2 mr squared. So I of the pulley is equal to 1/2 mass of the pulley times the radius of the pulley squared. So we can replace that into over here. We have 1/2 mr squared. And then we have this bit of angular acceleration, but over here we have the linear accelerations, and we're asked to find the linear acceleration. So is there a relationship between the angular acceleration and the linear acceleration? Hopefully you recall that the linear acceleration is equal to the angular acceleration multiplied by the radius. So we can replace the angular acceleration with the linear acceleration divided by the radius. So let's go ahead and do that over here. Okay, if we simplify a little bit here, we can see that R we could pull out T1 minus T2 on the left side. And on the right side, you'll see that one of the R's down here cancels out with one of the R's up there. So we get 1/2 mass times R times acceleration. Oh, looks like another thing can happen. We have an R here and an R here, and so the radius cancels out completely here. So what we have here is T1 minus T2 equals 1/2 times mass times A. So if you take a look at our unknowns at this point, because we have 3 equations, 1, 2, and 3, we have T1 as one unknown, we have T2 as another unknown, and then we have the acceleration as the third unknown. So we have 3 equations and 3 unknowns, and we should be able to solve that. So I'm looking at this and thinking, if I could rearrange this equation for T1 by itself, and also this equation for T2 by itself, that's relatively easy to do, then I can substitute both of these equations into the one down here for the pulley. So T1 would be equal to m1 times g minus m1a, and T2 would be equal to m2 times g plus m2 times a. So we're going to replace equation number 1 and equation number 2 into equation number 3. So T1, m1 times g minus m1 times a, minus T2, which is m2g plus m2a, equals 1/2 ma. Let's get rid of the brackets, and let's collect like terms of these 2 terms, bring them over to the right side, pull out a common factor of a on the right side, and then solving for a we'll get, and there's our symbolic equation, and all we have to do now at this point is substitute our numbers in. And then substituting our values in, we will find that our acceleration comes out to be 1.849, they'll just round that off to 1.85 meters per second squared. Okay, that's for part A. Let's take a look at now part B, or the second question that we can see in here. So part B is asking, how would your answer in the earlier question change if you had ignored the rotational inertia of the pulley? So if you basically had done this problem like what you did back in chapter 4 when we were studying pulleys and assumed that they were frictionless and massless. So what would change? Well, we would assume that if this was a frictionless and has no mass, then there would be no angular acceleration. And the two torques would essentially be equal to each other. The two tensions would be the same as each other, because there'd be no rotational inertia. You can imagine if m goes to 0, then the right side is 0, and well, the wheel actually would be accelerating angularly, but the problem is that there's no rotational inertia, and the two tensions would have to be equal to each other. So T1 and T2 would have to be essentially equal to each other in the above problem. So for part B, you could just say T1 and T2 would be equal to one another, so you would have M1G minus M1A equals M2G plus M2A, and then collect like terms on the right side, and then pull out a common denominator of A here, and then solving for the acceleration, we're going to get a very similar expression to over here, except there's no 1/2 m because we're assuming our pulley is massless. Now let's substitute our values in as we did before, and we get an answer of an acceleration of exactly 1.96 meters per second squared. And you can see that's a larger acceleration than what we had earlier because we assumed that the pulley had no mass and you weren't rotating that. So hopefully that makes sense, that you would have slightly larger acceleration if you neglected the pulley's effect if it had mass. Okay, let's go on to the last question in this one. And I've mislabeled this. This should be not a B, but should be part C now. So let's say M2 was initially on the ground and M1 was at rest 3 meters above it. And if the system were released, use the conservation of energy method to determine the speed, M1 just before it strikes the ground. Now, it says also to double check your answer using kinematics equations and the acceleration from part A. Let's show that part first. That's the easiest way. Since we went through all of this and found out the acceleration, why don't we go ahead and do that? Now, we're going to assume that we're going to get the real answer, assuming that we're not excluding the effect of the pulley not having mass. So let's use the answer that we got in part A, the acceleration of the masses. And if you were to solve this just using kinematics and you got part A completely correct, and you want to go use that answer to get part C, I'll just call this the sort of kinematics approach. You could just simply use v squared equals v initial squared plus 2a delta x. So the final speed squared would be equal to the initial speed, which is 0, plus 2 times the acceleration, which we got as 1.85 meters per second squared, times a distance of 3 meters. V squared would be equal to 11.094, etc. So if you take the square root of that, you'll get an answer of 3.33 meters per second. Okay, let's go over the energy approach. Let's say you hadn't done part A and you hadn't solved it using sort of forces. Let's say you were given this question and you're asked to find out the speed of the masses, and you didn't go through all of what you did in part A and found that acceleration, because it's got to be quite long. There's a way of doing this using sort of what we call the energy approach. So if you recall, the energy is conserved. So we need to assume some place is a zero gravitational potential energy point. Going back to our diagram, I'm going to assume right here at the very bottom on the ground here. So we're going to make the assumption that it's zero gravitational potential energy at this right at the surface here. So essentially M2 will have no potential energy initially, but M1 will have potential energy dependent on its 3 meters. By the way, it looks like it's drawn from the center of the body, so let's go ahead and change that 0 point to the middle of the body. So there you go, right through here. So the 3 meters is from the middle of this mass to the middle of that mass. So now let's apply the conservation of energy. And as we look at this, by the way, we're applying the conservation of energy. I'm going to be assuming that my system consists of M1 and M2 and the pulley. So this is all one big system. And we're going to assume that there are no non-conservative forces acting in the system like friction, so that we can assume that the mechanical energy of the system is conserved. So I'm just going to write energy initially is equal to energy finally. Or you could write it as kinetic energy initially plus potential energy initially equals kinetic energy finally plus the potential energy finally. And the kinetic energy initially is going to be 0 because both of the bodies are not moving. But, I'll just put in all the terms and I'll just show them canceling out. Or in retrospect, maybe I'll just write down the ones that matter because this would be quite lengthy. So the kinetic energy initially is 0 because both mass 1 and mass 2 both have initial speed of 0. Furthermore, the rotational kinetic energy is 0 because they're not moving rotationally at all. So really all you have is the initial potential energy of m1 that's hanging a little bit higher at 3 meters above. So we're going to write that as m1 times g times h. And then later on, we have the kinetic energy. Now we do have all the bodies are rotating now, so we have and moving. So we have the translational kinetic energies. That's 1/2 m1 v1 final squared. We have the translational kinetic energy of m2 v2 final squared. Plus we have the rotational kinetic energy of the pulleys. That's 1/2 I omega squared. And then you also have the potential energy of m2 that has gone up. m2 times g. m1 times g times h is 0 because remember now m1 is now on the ground and m2 is sitting up 3 meters above. Well, not sitting, it's moving actually at that point. And v1 final and v2 final are really the same because it's both moving, they're attached to the same string, so they both have the same velocity. So let's just rewrite v1 final, v2 final as just v final. So we're solving for this final velocity here. And we know m1 and m2 and h is 3 meters and g. We need to replace I and omega. If you recall earlier, I for the pulley was the same for I for a disk, which is 1/2 mr squared. And the angular velocity, if you remember, the linear velocity is really the angular velocity multiplied by the radius. So the angular velocity omega can be replaced with the linear velocity v, or v final actually, divided by the radius r. So let's make these substitutions into the above equation. And you should notice things that cancel out. For example, this r is going to be squared, and that will cancel out with this completely. And we'll have 1/4 m v final squared. And I'll collect like terms of v final here, and here, and here, and put this term over here to the left side. So I've taken out a common factor of v final squared divided by 2, so that'll have m1 and m2 in brackets, plus also 1/2 of m. And now if we solve for v final algebraically, and we get this nice equation. And then we could substitute if we wish, putting in our values for m1, m2, and m and h of 3 meters. And plugging into your calculator, you'll get an answer of 3.33 meters per second. And that's it for this rather long problem.